Alright, today's question is edit distance, and they give us two words, word 1 and word 2, and we want to find the minimum number of operations to go from word 1 to word 2. And the type of operations we're allowed here is insert, delete, and replace. Now notice in the question here they say minimum, which means that this is really an optimization problem. And one of the tools we have for dealing with optimization problem is the idea of dynamic programming, where when you solve a subproblem, we can use that subproblem to solve the original problem. So let's see how that takes place here. So suppose we want to solve the problem of how to go from got to Ross. So we want to solve the edit distance of going from got to Ross. And suppose we know the solution to a subproblem already, and in this case, our subproblem will be from go to row. So we already know how to go from go to row. And in fact, if we try and solve it, all we have to do here is replace this g with an r. So that means this has an edit distance of 1. Okay, so how do we use that to solve this original question? What we can do is something like we go from got into rot. And here you can see that we use the subproblem of go to row, and we didn't touch the rest of this string, which means that this has an edit distance of 1. So the same as the subproblem. And then after we have completed it, all we have to do is replace this t with an s to get our final solution of Ross. So we just added another operation here. So that means here, in total, our edit distance is going to be equal to 2. So you can see that in this question, we can use dynamic programming where we solve this subproblem to solve our original question. Now it's a little bit more complicated than that because we have 3 operations that we can be dealing with. We can deal with insert, delete, or replace. So let's see how each one of these, how solving a subproblem can help. So in the first case, we have insert. So with insert, what we have is we know the subproblem of how to go from horse into row. So there's some edit distance of going from horse to row. And then all we have to do here is we just have to insert an s at the very end to get Ross. So we plus 1 here. And there it is, there's the solution. Okay, so what about with delete? So with delete, the idea is that we know the subproblem of going from horse without an e into Ross. Then in our original question, all we have to do is for the very first step, when we have horse, we just want to delete e. So remove this e gives us this horse, which is part of our subproblem, and we know how to convert from here into Ross. So it'll be 1 plus whatever the edit distance of this subproblem is. Now the third case, it's a little bit tricky. There's actually 2 cases here, but for now I'll just go over the first one, which will be with respect to this example here. So what we want to do here is we know the subproblem of going from horse into row. And then all we do is we carry over this e from the beginning into our subproblem, and then we just add on 1 step here. So this has some edit distance, and then we just replace this e with an s to get Ross. Okay, so this question is asking us about the minimum. So what's the minimum number of operations? So all you have to do is we'll just take the minimum of each of these 3 possible solutions, right? So we just take the minimum of 1, 2, and 3. And this will give us our edit distance for horse into Ross. Now something cool you'll notice here is that this horse to row subproblem corresponds to this section right here. So horse to row. And then we'll look at this delete as well. So this delete corresponds to HRS into ROS. And then finally, we have our replace, which is going to be HRS into RO. So I'm going to copy this and then see where they look like on a grid. So on a grid, where each cell means how do you convert from, for example, let's say this cell right here. This cell right here tells me how do I convert from horse into row. So our goal is to figure out the solution to this. How do I go from horse into Ross? And we just said that in order to solve that problem, we need to solve these three subproblems and pick the minimum plus 1 out of them. So here, the red one, so actually the green one, is going to be addition. And that's going to be this problem right here. So this is our addition operation. So what we do is we solve this subproblem, and then we tack on this s. We add this s at the very end. And then the other one we have here is delete, which will be this subproblem right here. And what we do is we delete this e first. We delete this e first, and then we convert from horse into Ross. And then lastly, we have substitution. So this is substitution, which means we go from horse into row, and then we substitute e with s in order to get to our solution. So you can see here that to solve this problem, we need to solve these three subproblems. And to solve this problem, we need to solve these three, and it kind of works backwards like that. So that also means that we can start from the very first element here and fill up our grid until we get to the very end, and then we can just return the end, so return the last element of this grid. So let's do that instead. Let's work through what this value should be. Now this value is an edge case because there is no left top and top left neighbor to choose the minimum from. So what I'll do is I'll introduce the idea of an empty string. Now how do you go from an empty string to an empty string? Well, you don't do anything. So this will be 0 operations. How do you go from an empty string to a letter h? You just insert h, right? You just add 1. So this will have an edit operation of 1, 2, 3, 4, 5. Similarly, going down, this will have an edit operation of 0, 1, 2, 3. And now we have all the pieces we need in order to solve this first cell right here. So we take the minimum, 0 here, and then we just add 1 to it to get 1. And similarly here, we can take either one of these minimums, we add 1 to get 2. And then here, we might be tempted to say, we just pick one of these and we add 3. But there's actually a special case happening here, which is this substitution happening right here, when these two letters are exactly the same. So let's take a look at what I'm talking about. So in a normal replacement, or I've been calling it substitution, but replacement, substitution, it goes something like this. So we have horse into row, and then we substituted something to get to Ross. Now what do we have in this case? In this case, we have HOR into just R. So we have the case of HOR, we want to get to just R, and we know the subproblem of how to go from HO. So we know this subproblem here, which is how to go from HO into the empty string. So we know how to go from HO into nothing. And you can see here, when we do this edit distance, after we've done this, because the last letter is the same, there is no extra +1 to be done to do this substitution or this replacement of e to s at the end, because we're already happy with what the last letter is. So in this case, the minimum, instead of here +1, it's actually going to be just +0. Right? So it's just going to be +0, and instead of 3, this edit distance will remain at 2. So this happens whenever we have the same last letter. We have to take in account of this special case that could occur. Okay, so continuing on with the rest of here, we have the minimum is 2, so we have 3, and then 3 here, we have 4. Okay, and then here we have 2, and again we have this special case of O to O, so that means we can pull this 1 down and see if it's the most minimum, in which case it is, so we have +0 here, so this will still remain at 1. Okay, continuing on, here's the minimum, we have 2, we have 3 here, and then here we have 4. Okay, now with S, we have this 2 is the minimum, so now we have 3, and here we have this 1 is the minimum, so we have 2, We have 2 here, and notice that we have another case of s and s being the same. So here, let's check 2 plus 0 is indeed the minimum, so we'll pull in 2 here, and then that gives us our final solution here of 2 being the minimum, and we will return 3 as the solution to this problem. And you can see when we take a look at the example that they give us, the answer is indeed 3. Okay, so let's try and code this out. And there's actually an optimization I'll do at the end of this for how to make our data structure better, but let's just go with the simpler version to start off with. So we have int n will be the length of our first word, int m will be the length of our second word, and already we can do a quick check here. If n equals 0, we can return m. So if word 1 is empty, then just insert every letter in word 2 to convert it into word 2. If m equals 0, so if m equals 0, return n. So if we want to convert word 1 into the empty string, then just delete every character in word 1. Okay, so these are the 2 edge cases, and now we'll create our grid. I'll call it DP for dynamic programming. And this will have n plus 1 and m plus 1 size. And this is basically because we have a row. So here is our n, so ROS, but then we plus 1 for this empty string that we're using here. And then similarly, here we have m, and then we plus 1 for this empty string that we're using here. Okay, and then the first step that we'll do is we'll create this first row right here. Right. So this first row is going to be int column. So for int column equals 0, column less than n plus 1, column plus plus, dp at the 0th row at this column is going to be equal to column itself. So that will give us a running from 0, 1, 2, 3, 4, 5. Nice. Okay, so from that, this will be our edge case for the 0th row. We can start with the first row. So row is going to be less than n plus 1, row plus plus. Okay, now here, we also have another edge case, which is going to be the first column. So the first column is always going to be equal to whatever row that we're on. So so you can see here is row 0, row 1, row 2, row 3. So the first column is always equal to the same thing as the row that we're on, and here are our columns. Okay, so now here we have that dp at this row, the 0th column is always equal to the row. And now we can do for int column equals 1, column less than n plus 1, column plus plus. And now we have the 3 subproblems that we need. So if we had A, B, C here, and D, we know now how to solve this because we have B, we have A, and we have D solved already. Okay, so here we'll have dp at row at column is going to be equal to the math at minimum of either the addition operation or the insert operation or the removal operation. So this is going to be dp at the previous row at the same column. So this is going to be the insert operation, or we can choose the removal, which will be at the same row but at the previous column. And then we'll add 1 to insert or remove as necessary. Now we want to handle the replacement. And the replacement, it's a little bit weird because there's an edge case here of whether or not the last characters are the same. So if word 1, char at row minus 1, is equal to word 2, char at col minus 1, then there's a different replacement than if, then we don't need to, so here we don't need to do replacement. Here we need to do the replacement. Now this row minus 1 and this column minus 1 just comes from the fact that because we added 1 in the beginning, now our word indexes are offset by 1. So a quick example here, here we're on row 1, but we're actually reading index 0. So that's why I gave it an offset of minus 1. Okay, so that means here we have the potential that the solution is we have an even better solution here. And that's going to be the dp at the previous row at the previous column. Versus here, the third operation that we're comparing is going to be also the same, col -1, but we have to do the replacement at the very end, so that increases our count, our edit operation, by 1. Okay, and at this point, when we filled out the grid, all we have to do is we just return the last element in this grid, right? So the last element right here, which is going to be at the nth row and at the mth column. And if I typed everything correctly, we should have our first solution. Cool. So in our first solution, you can see here that we have a runtime of O of n times m, because we're iterating through every single cell in the grid. And our space is also going to be n times n. Now what I'll show you is I can actually make this space equal to the minimum of m or n. And this is how we're going to do it. So the way that we'll do it is we want to notice that at every point when we're trying to calculate, for example, let's say we're trying to calculate the answer to this, we just needed to know 3 values. We did not need to know the entire grid of solved solutions. We just needed to know these 3 values. And these 3 values can be categorized as the previous row and the previous calculation that I just did. So instead of storing everything into a grid, I just need the previous row and the previous calculation that I just did. So let's see how we can make this change. So first here, instead of a full grid, we'll just do the previous row. And there will be no more rows. We just have the same column count. So this will be our initializing our previous row. So here, instead of the 0th row, we'll just have previous row. Okay, so now when we're trying to calculate our first column, this is actually going to be the edge case of int previous is equal to row. So what was the previous calculation that I just did? So now here we can start calculating our edit distance. I'm not going to write directly back into our previous row, and you'll see why in a little bit. So our distance for our solution for this cell right here is going to be, so row -1 is the previous row, and then this is going to be the same row but the previous calculation, right? So this is actually going to be previous right here. So we can replace this with distance, and again this can be replaced with distance, and then now this is going to be the previous row at col -1, and then very similarly we'll do the same thing here, and then this will be previous row. Okay, so now we have the solution for this cell, but we haven't written anything back into previous row yet. So let's see how we can do that. So we have A, B, C, and D, and let's say we just figured out that this distance, so let's say this distance is equal to E, this E belongs here. Now what I'm not going to do is rewrite, so this is our previous row, and this is our previous D right here. So this is previous. What I'm not going to do is overwrite this E on top of the previous row right away, because when I'm trying to solve the next solution, which is this right here, I still need to know that this was in fact B. So I cannot overwrite it right away, but what I can overwrite is this previous into this location of previous row up there. So now I can forget about this, and then I can bump this up to E, and now when I'm trying to solve the next cell, I still have the correct 3 subproblems here. So what I need to do is I need to set previous row at column -1 is going to be equal to previous, and now I can bump this previous forward to what I just calculated for the next calculation. Okay, so we're kind of doing like this delayed writing into our previous row. So because of that, when we exit out of this for loop, we need to make sure that our last element in our previous row is we're still going to write to it. So we don't want to forget to write the very last this. So when we solve that this is F and we finish our loop, we need to remember that we need to write E and we need to write F here. So that's what this line does right here. Make sure that we write this F. Okay, and now at the very end, all we have to do is return the very last calculation we did, which is going to be previous row at M. So let's try running this code. Cool. And now the final solution, because now we have a space of minimum. So right now what we have is O of m for this space because we're doing this m. Now how do I guarantee that it's the minimum of m and n? All we have to do is this very simple change here where we go, if m is greater than n, I want to return min distance of these parameters flipped around. And what this achieves is right now here, we're doing horse to Ross. But instead, I'm asking, let's solve how to go from Ross to horse, which will have the same edit distance. So it's going to be the same solution. But here you can see our previous row is going to become this instead. This becomes our previous row, and this is a much smaller space than storing this yellow box right here. And that's how we will achieve our minimum of m and n. Okay, let's submit and truly make sure that everything was correct. All right. Okay, so that's the end of edit distance, and I'll see you on the next one.